Hello, I'm Philip Muggleston, and in this series of videos we're covering the predictive capabilities native to SAP HANA. In this video we're going to be looking at anomaly detection, essentially looking for patterns that do not conform to established behaviors. Now typically this is part of outlier analysis. However, we do this using clustering techniques, specifically k-means that we've seen in a previous video. So it's a good moment to cover the anomaly detection capabilities available with the PAL. So why would we want to look for outliers? There are two key areas. One is we may want to identify fraud, for example, looking for things that aren't typical. Maybe it means someone's doing something they shouldn't be. But also, as part of our initial preparation before further analysis, we might want to look and remove outliers that are maybe going to skew the analysis we want to perform. The anomaly detection is undirected. What that means is there's no need to actually train the model first and then apply it. So you don't need to provide some real examples, for example, of fraud or real outliers to train it first. In fact, the algorithm uses the k-means approach to cluster data together and then try to identify outliers that don't really fit well into those clusters. So this is undirected data mining. So let's have a look at some real data to get an understanding of what we want to be doing. Let's browse the customer data that we already were looking at in the previous k-means examples. We can see that for 150 customers, we've got lifetime spend, new spend, and notably income and loyalty factors. And we can just chart this. Let's go and put the ID and income and loyalty and make a scatter plot. So now we can see the information, we can see the ID, we could also maybe add customer to get a bit more idea of who's who. So we've got the different IDs of different customers. And if we look, we can see, for example, that's customer, that's Henry Rufut. What we can see here, we've got data which seems to naturally fall into two, or actually we saw three different clusters. But different from the previous examples, I've added one extra row here, which is actually customer 151, known as Anomaly IAM. So what we're going to hope to find is when we run the anomaly detection algorithm, we're hoping we're going to identify this because it doesn't seem to fit into the actual three. There are three natural clusters for this data to fall into. Now obviously here we're looking just at 2 dimensions, but in reality we have 4 different dimensions that are being used for the clustering process. So having taken a look at that, we can go to the code, and as always I've got some code pre-prepared to save us a bit of time. Again, if you've not seen the Getting Started or the Key Concept videos, or indeed the K-means videos, I recommend you watch those first because we're building on that knowledge. So the first thing is we need to create the algorithm. We need to effectively create a procedure in the _sys_AFL schema. So here's the code. Now effectively the data we're going to input to this is pretty much the same as we did to k-means. In fact, this procedure will perform a k-means for us as it's working. And the parameter table is the standard one. And then there is one output table that we use with this. And in fact, it's identical to the input data. So we don't need to create a specific table type for it. We can use a table type for the input data. But here we're saying the third item is out. We're going to create a procedure that we will call PAL_AD for anomaly detection, and we need to use the anomaly detection. And as always, the reference guide for the PAL gives you the full details on all of the syntax that you might need and the options that you might have. So let's run that code to create the procedure. The procedure is now created. And then for our application side, here we want to set up the input data, and again this procedure, it requires specific columns and to be in a certain order. So the easy way to do that is to create a view from our input data, because in our input data we had the customer column as well. So we've left that out here. We just need the single ID and then the 4 independent variables. We've got the parameter table and the results table. The results table, as I said, is just like the input data, so we can actually use the table type that we already had. So we can run that code. Before we do that, we'll just go through some of the parameters. So for anomaly detection, we have a number of parameters. Many of them are the same as you see with k-means, because actually we're going to perform a k-means as part of this, so it can identify the anomalies relative to that. So for example, the group number tells us the number of clusters that we want to create, etc., etc. What we can also see though are two new parameters called outlier percentage and outlier define. And these are specific to the anomaly detection approach. The outlier percentage, it has a default of 10%. We're showing these as decimals, so 0.1 would be 10%. Here we've set it at 1%. It basically says of all the data we're going to feed, what percentage of that data should be identified as anomalies. So we said 1%, so only 1% out of that 150 or so customers we would want to be identified as anomalies. And you can tweak and customize that as you want. And the second area that's quite important is the outlier define. And the outlier define has two values you can put, 1 or 2. A value of 1 basically says identify an outlier based on the distance that that customer or that ID is from the cluster that it's being assigned to. Whereas setting the outlier define to 2 says identify outliers based on the distance that customer is from the center of all the customers that have been, all the clusters that have been defined. We'll see more examples of that as we go forward. So let's now run that code to set it up. Okay, that's now run, and now we're ready to start running some analysis. So in this case, it's the first run. We can simply run the procedure. So let's run it against our input data. So we're looking for 1% of the data to be outliers, and we're looking at it based on the definition of 1, which means looking the maximum distance from the center of the cluster that the customer has been assigned to. So let's have a look at the results. Let's just browse our results table. So now we can see, it's identified one outlier, and that is ID 151, and we can see the values for 151. So if we go back to our little view here and look, actually it's this one here. We can see this is 151. It's customer anomaly I am, income 2.5, loyalty 0.75. So it's identified that this one doesn't really seem to fit naturally into the customers. Effectively, it's the furthest from the center of the first cluster, and it's the furthest from the center of the second and third clusters. So that's what that distance refers to. That's what the outlier define is. It's based on different from the cluster it's assigned to. So if we were using the outlier define of 2, then the algorithm would be slightly different in that you would be looking at this being the furthest distance from the center of this cluster, and this cluster here. So it's actually all of the clusters that it's separate from. So we've now seen one simple example. What we could also do is maybe tweak this a little bit. So for example, we might want to see a little bit more in terms of outliers. So for example, we could set that to maybe 2 or even 3%. So let's go 0.03 representing 3%. Let's update that and let's run the analysis again, and we'll see what we get presented with. So this time he's actually identified 4 different. We've still got 151, but because we asked for a larger number of outliers, he's actually gone, the algorithm has gone and looked in more detail to find the next best likelihood of what outliers would be, the next best outliers in the data. And he's identified another 3 different customers. Because we said we want to have actually 3% of the data should be identified as being outliers. And what we could also do here is maybe set the value for outlier defined to 2. So instead of looking at outliers based on the individual cluster they were assigned to, which are the outliers that are well away, the furthest away from all of the different cluster centers, all the different clusters that have been defined. So we can set that one to 2 and run. Then of course retruncate the table, call the procedure, look at the results. And this time we see we get 4 as well, but however the IDs have changed. So this time we're using a slightly different method. We've identified some different customers in this case that are potentially outliers. So what we've seen is the ability to use the predictive analysis library to perform anomaly detection. The way that's done is based on the k-means algorithm by naturally clustering the data, assigning every customer into a cluster, and then looking either for outliers based on customers that don't fit the center of the cluster or the furthest away from the center of the cluster they were assigned to, or optionally, with outlier defined set to 2, that are furthest away from the center of all the different clusters that have been set up through the algorithm.